Welcome back to machine learning. This video will cover neural networks. Neural networks are very closely related to the perceptron. We know that the perceptron is a linear model. It works well on linearly separable data, and we can set a stopping point for non-linearly separated data using a maximum number of epochs. We like linear models because they're simple, and we always want to describe our data using the simplest model possible. The perceptron can be used to represent several logical functions, including and or. But it can't be used to represent XOR because the data is not linearly separable. So even though this is a very simple logical function, the perceptron can't represent it. So we need something a little more powerful to represent complex functions. That's where neural networks come in. They're basically just stacked perceptrons with an added nonlinearity. They look like this. We have two sets of perceptrons. At the first layer, we have d data dimensions, so our feature vectors are d-dimensional. And we connect every feature to h1 and then to h2 and so on. So you can think of each h as being its own perceptron. There are capital H number of perceptrons at the first layer. Then each h is connected to this out node. So there is one final perceptron at the top. Each perceptron has its own set of weights and bias. We refer to the weights for each layer using superscripts and the weights within a layer using subscripts. In the first layer, we have two subscripts. First, I tells us where we're coming from, which feature dimension, and the second, J, tells us where we're going, which hidden unit. So W sub ij is coming from the ith feature and going to the jth hidden node. At the second layer, we have one subscript since there's only one place to go. The subscript here refers to the hidden unit where the weight is coming from. The output is calculated as the dot product of the weights in the second layer and the activations of the hidden units. For simplicity, we're ignoring B for now. Don't worry about it too much. Each hidden unit's activation is calculated just like in a perceptron, with the dot product of the weights and the input. Here, the notation is a little bit different. We see W superscript 1 subscript colon comma J, which means all the weights coming into hidden unit J. Again, we're ignoring B. We can take the equation for H sub J and substitute it into the equation for the output to get one equation for the output. First, we have to change the notation from dot product to sum of products. Then we replace H sub J with our equation from before, and we have a single equation for the output. This seems cool, but it's actually completely uninteresting because it's just a linear function, just like the perceptron, because it's simply a combination of linear functions. And a linear combination of linear functions is itself linear. That means that this model, as it's shown here, is no more powerful than a perceptron. So where does the nonlinearity come into play? We use a nonlinear activation function at the hidden units. We'll call it A. So we take the dot product as usual and apply A to the result. We can also apply a nonlinear activation function to the output. Now typically we apply the same function to all nodes in a layer, but this is not a requirement. It just makes the derivatives easier to deal with when we learn the parameters for the model. What kind of nonlinear activation do we typically use? A common choice is the sigmoid function. It looks like this. Basically, it takes values from negative infinity to infinity and squashes them to be between 0 and 1. Another common choice is the tan h function. It's very similar to the sigmoid function, taking values from negative infinity to infinity and squashing them down between negative 1 and 1. More recently, popular choice for deep networks is the rectified linear unit, or ReLU. Now the ReLU function is very simple. It takes values and either leaves them as they are or sets them to 0. So if the value is negative, it becomes 0, and if it's positive, it is just itself. So basically, all it does is get rid of negative values. In practice, this turns out to be a very useful activation function. Now that we understand the structure and some options for nonlinear activation functions, we can talk about learning. Just like with the perceptron, we want to learn the weights and the bias. Even though we're ignoring the bias for now, it's still in there, but we can think of it as a weight. We learn the weights for a neural network using a technique called back propagation. It's a fancy term which just means that we use gradient descent and the chain rule from calculus. This is where everything comes together. We learned about the perceptron, then we learned about linear classifiers and how to train them using loss functions and gradient descent. Now we combine these two things and we get neural networks. We need a loss function so we can perform gradient descent to get the weights. Remember this loss function? It's the squared loss function, or Euclidean loss. This is typically used for regression problems, that is, predicting real values. If we use the terminology from our network, we would replace y hat with out. Expanding this, like we did before, we get the following. Remember that the network output is just a function of the input and the weights. Now we need to take the derivative of this function with respect to our weights so we can update them. Let's take the derivative with respect to the second layer of weights, w superscript 2. Let's take one weight to start with, w2, 1. We take 2 from the exponent and bring it out in front, and then take the derivative of the inside. W21 is only in the W21H1 term, and the derivative of that is negative H1. So all in all, the derivative of L with respect to W21 is negative 2 H1 y minus out. If we generalize this to all W2 sub j, we get the following partial derivative, negative 2 times H sub j times y minus out. That was pretty painless. Let's look at it a slightly different way. We can see the chain rule in action here. If we take the derivative of L with respect to the output, or y hat, then we get this, negative 2 times y minus out. Now, if we take the partial derivative of the output with respect to W2 sub j, we get H sub j. The chain rule states that we can multiply these two together and get the partial derivative of L with respect to W2j, like so. So this is much nicer to look at and deal with than expanding the full loss function and finding the W that we're looking for in order to calculate the partial derivative. This will come even more in handy when we look at the first layer of weights. If we look at each part separately, we have the loss with y minus out squared. We have out, which is the dot product of W2 with H, and can be expanded like this. And then we have H sub j, which is the dot product between all the weights going to H sub j and the input x, which is expanded like this. We can use the chain rule to find the update for W1. We take the partial derivative of the loss with respect to the output and we get negative 2 times y minus out. Then we take the partial derivative of the output with respect to H sub j, and we get W1 sub j. Finally, W2 sub j. Finally, we take the partial derivative of H sub j with respect to W1 sub ij, and this gives us X sub I, or the ith feature of the input sample. We multiply all of these together and we get the partial derivative of the loss with respect to the weight W1 sub ij. Now we have all the partial derivatives we need to do the update. Remember that this is not the update, but we use these and we plug them into the gradient descent update equation. The whole point of a neural network was to introduce nonlinearity. So how do we handle derivatives when we have an activation function? Here we have an activation function A at the output layer, and all we do is change the partial derivative of the output with respect to the second layer of weights, that is, d out dw2 sub j. We see that A prime here is multiplied by H sub j. The derivative of the outside is multiplied by the derivative of the inside. Similarly, if there's an activation function at the hidden layer, here we have A sub 2 as the activation function at the output layer and A sub 1 as the activation at the hidden layer. So we take the derivative of the loss with respect to the output and we get the same thing we've always gotten. Then we take the derivative of the output with respect to H sub j and we get A2 prime times W2 sub j. Then we take the partial of h sub j with respect to w1 sub ij, which is a1 prime times x sub I. Multiplying all the partial derivatives together gives us our final partial derivative of L with respect to w1 ij. Remember that backpropagation is just the gradient descent rule plus the chain rule. Now that we have our partial derivatives, we can update our weights like this using our gradient descent equation. So now we know how to learn. How do we start learning? How do we initialize? With the perceptron, we just started with both w and b being equal to 0. Let's see how that would work here. If we assume we have a nonlinear activation at the hidden nodes, but not at the output, then we get the following. Each hidden node will have the same value because all weights are 0 and the dot product of w and x is 0. So the hidden units will all have the value of a sub 1, 0. And out will have a value of 0 since the dot product of h with w2 will be 0. So now we update w2. Remember all these fun equations? Let's do that. We get the partial derivative of out with respect to w2 sub j is negative 2 times y times h sub j. And so w2 sub j is updated to be 2 times eta times y times h sub j. Now let's update w1. Remember these fun equations? We get the partial derivative of the output with respect to w1 ij is equal to 0. This is because our multiplication during the chain rule, we multiply w2 sub j, and that is 0. Notice we don't use the updated value of w2 sub j, but rather the one we had before we began the update. So using our gradient descent update, our new w1 is 0. If we repeat this process, we'll find that each of the hidden units learns the same thing, as all of the weights for the first layer are updated in the same way, and all of the weights of the second layer are also updated in the same way. I work out partially here to show you this. Make sure to convince yourself of this. Based on our previous update, these are our new W values and hidden layer values and the output value. We update W2 first and we get this. What's interesting about this is that each W2 sub j is being updated in the same way. Similarly, with W1, we get the following partial derivatives. We can see that for each j in W1 sub j, ij, the update will be the same. That means that for each input feature, the weight going from that feature to each hidden node will be the same. Hence, the hidden nodes will all learn the same functions. This is obviously not what we want. Otherwise, why do we have all these hidden nodes? So what can be done in practice? Well, in practice, we initialize the weights randomly with small values. This works well because it basically places you at a random point in the function from which to begin the gradient descent process. And that's basically it for neural networks. We discussed the model, which is the network itself consisting of a set of weights, and the algorithm for training the model is backpropagation. It's called backpropagation because you're taking the error at the end and you're propagating it back through the network. The next video will cover deep learning and convolutional neural networks.